So our energy change is the difference between our final and our initial states. So exothermic energy is out of the system. Energy going into the system is endothermic. Now, when we talk about our system, we've got a couple of different ways to describe our system and our surroundings relative to each other. So here we've got a system where the reaction mixture is the system and the surroundings are the flask, the room, the air, and the rest of the universe. We've got three types of system, and we're going to call them open, closed, and isolated. So our three types of system. In an open system, you have free exchange of mass and energy. So this would be our open system. This guy's open. Right? Energy is able to flow into or out of the flask freely. We're also able to exchange mass or matter, so water vapor can exit the flask. So when you guys do a calorimetry experiment with a coffee cup calorimeter or a simple calorimeter, you're going to be looking at a system that is going to be able to exchange with the atmosphere, so you're able to do PV work. In a closed system, this is this guy over here where we've got the little cork on it, right? We can exchange energy into and out of the flask, but no exchange of matter. Right? And then you've got an isolated system where we've got no exchange either of heat, right? Can't go in, can't go out, right? This guy's insulated, and it's closed. Our source of heat in exothermic reactions, heat is expended based on the difference in potential energies between products and reactants. Energy gained by the surroundings must be equal to the energy lost by our system. This is our first law of thermodynamics, right? We're not going to have energy created or destroyed. We can only change its form, right? So if I lose energy in my system, it's got to be equal and opposite to the amount of energy that is gained by the surroundings. In an exothermic reaction, and that's most of our reactions, some of the potential energy is being converted into thermal energy or heat. And so if we've got, in this diagram, we've got a potential energy diagram where energy is on our y-axis. Right? And we've got a reaction between 2 moles of oxygen and 1 mole of methane. Those are reactants which have a particular potential energy. We then have products that are formed, 2 moles of water and 1 mole of CO2. And so our change in energy is going from a higher state with our reactants to a lower energy state for our products. This change in energy is going from higher to lower, so energy is released to the surroundings as heat. This is an exothermic reaction. And most of our reactions, like I said, are going to be exothermic. This is also pointing out that this big energy difference here is why we see things that are highly reactive reagents, right, like hydrogen and oxygen to form water. The general rule of thumb is that the more reactive our reagents, the more stable our products are going to be. And we're going to have a large exothermic process that goes with that. But once we form these products, they're low energy and nice and stable. So we have lost energy in our system. We're going from high energy to low energy. That energy had to go somewhere. It's going to be released to the surroundings as heat. If I were to draw a reaction energy diagram for an exothermic reaction, I would have my reactants over here. They're going to go through some activation energy. It's going to take a little bit of energy to get this reaction going. Right? And we will talk about that in the thermodynamic chapter later on in the next course in the sequence. But if you think about something like so in that reaction between hydrogen and oxygen, you would need like a little bit of a spark to kind of get things going. That's going to be things that kick up the molecules over this activation energy barrier. The energy would be released as you form the products, which have lower energy. And our sign, our delta H, or change in enthalpy, or our change in energy, is going to be negative, right? Because we've gone from high energy to low energy. So this is going to result in heat exiting the system. In an endothermic energy level diagram, we're going to start off with low energy reactants. We still have to go up over an activation barrier, but we're going to end up with products that are higher energy. So the reactants have less potential energy than the products. So in order for this reaction to happen, I need to put energy into my system. My delta H, my change in energy for my system, for my chemical reaction, is positive. It's taking energy out of the surroundings to drive that chemical reaction. So let's do a quick concept check. So is the freezing of water an endothermic or an exothermic process? Pause. Think of. Okay, so I've got liquid water, and if I want that to turn into an ice cube, do I need to get this water colder or hotter? Well, if I want to get it colder, right, so I'm going from a high temperature to a low temperature, I need to remove energy. So my energy has to go out of this water into the surroundings. So this guy is going to be an exothermic process, right? Because water is losing energy to the surroundings. The temperature of the water, the energy in the water is going down when we form ice. All right, so let's do another one. Let's classify each process as exothermic or endothermic, and we'll explain. Okay? If a person's hand becomes cold upon touching ice, that is going to be an exothermic process for the hand. So energy is being lost by the hand. It's going into the water. It will be endothermic for the ice. If ice gets warmer upon touching it, that's going to be endothermic. This guy was exothermic. Water is boiling in a kettle by being heated on a stove. The energy is being transferred from my surroundings, from my stove, into the water. That guy's going to be endothermic. If water vapor condenses on a cold pipe, you've gone from a gas phase, high energy, fast-moving molecules to something cold, or slower-moving liquid molecules. That's going to be exothermic. If ice cream is melting, it's going from a solid to a liquid. To do that, it has to absorb heat. That's going to be an endothermic process. Right? So for each of the following, we're going to define its system and the surroundings and give a direction for the energy transfer. Right, so we've got a Bunsen burner in the first case. Right? And so methane is burning, so we've got a combustion of methane, CH4 and O2. Right? So for my CH4 and O2, this is going to be an exothermic process. So this is going to be exothermic. This is my system. Right? The rest of the room will be my surroundings. Right? And as far as the room goes, the room is going to get hotter, and it's absorbing heat. It's going to be endothermic. Right? If I have water droplets on the skin and they're getting vaporized, right? Heat is going from the skin into the water. So from the water, which is our system, right, that's going to be endothermic for the water. And it's going to be exothermic for the skin. So the energy from our surroundings, right, which is our skin, the rest of the universe, is going into the water droplet as it's evaporating. So hydrogen and oxygen gas react violently to form water. Explain. Which is lower in energy, a mixture of hydrogen and oxygen gas or water? Well, if we draw the reaction diagram for that, we know it's going to be generically one of these exothermic energy reaction diagrams, because we said we're going to have some sort of change in energy or change in enthalpy. It's the same thing. We're using them interchangeably, right? And we know it's going to be exothermic, so we've got to have this negative enthalpy change, right? Which means that my reactants are going to be higher in energy than my products. The law of conservation of energy, which is often called the first law of dynamics, says that the energy of our universe is constant. The internal energy, or E, of a system is just the sum of the kinetic and potential energies of all the particles in the system. If we look at the internal energy of a system, it's going to be the sum of both work, heat, or both. So our internal energy change is going to be related to my heat change and how much work I can do. And you guys are probably all familiar with this. If you've ever driven a car, what happens to the engine? It's going to get hot. You're able to do some work, right? So my change in my internal energy is going to be related to heat and to work. Defining the energy from the perspective of the surroundings we're going to say that our change in energy is equal to Q minus W prime. And that's the work from the surroundings point of view. Right? And they're going to comprise a number indicating the magnitude of change and a sign indicating the direction of flow of energy. Right? In an endothermic process, we'll have Q is equal to plus X. It's going to be increasing the energy of the system. And in an exothermic process, Q is going to be equal to minus X, a decrease in the energy of the system. So we can calculate the change in energy for a system undergoing an endothermic process. So it's going into the system in which 15.6 kilojoules of heat flows. So this is going to give us our magnitude of our heat. And where 1.4 kilojoules of work is done on the system. Right, so when you see these, your keywords that you're looking for to determine the sign are you're looking for things like endo or exothermic. And if you're talking about work, you want to see is done on the system or is done by the system. So if work is done on the system, the energy is going into the work, into the system, it'll be positive. If work is done by the system on something else, like a piston pushes, so you have an explosion and that piston pushes against an external force, like say the crankshaft of your car, that's going to be negative. You're losing that energy to work outside of your system. Right? So you're going to look for the is done and you're going to look for endo or exothermic. Right? So we're going to use our equation that says our change in energy is going to be related to Q and W. Right? W is our work, Q is our quantity of heat. So our Q is going to be plus 15.6 because it was endothermic. So endothermic means it's going to be a plus. Exothermic would have a minus. Work is done on the system. That means our energy is transferred in. So our work is going to be positive as well. So all we've got to do is say our change in energy is going to be plus 15.6 kilojoules plus positive 1.4 kilojoules and gives us 17 kilojoules total. Which means that our system has gained a total of 17 kilojoules of energy. Now, do they both have to be positive? No. They could both be negative. Q could be positive, W could be negative. Q could be negative, W could be positive. Right? You got to look to see what the problem is setting up for you to determine what the overall energy change is. And another thing you want to be careful of is making sure that you've got the right units. So this guy is in kilojoules for Q, and this guy is in kilojoules for W. Make sure that they are in the right units, especially when you start doing some of these calorimetry problems later on, in which case some of the things are going to be in joules, and some of the things will be in kilojoules. Either do all kilojoules or all joules, and then if you need to, reconvert at the end. Okay? So if you've got a gas, it can do work through expansion. So locomotion occurs through the heating of gases by combustion, and expansion of gases pushed back on the piston. And we will see this guy showing up later on as Charles' law, right? Or it is the thing that makes your internal combustion engine go. Right? So we use Charles' law to generate electricity. We use Charles' law to move automobiles, to do any of the things that have a motor that is a fossil fuel powered motor. And for a lot of those things that are electrical motors, you're still burning fossil fuels. You're still taking advantage of Charles' law to do that by displacing a piston, right? Or spinning a turbine. So consider a gas with a movable piston with a force F acting on the area of a piston P. Well, remember our pressure is going to be force per unit area, right? Our pressure is force per unit area. So if we've got an expansion process, right? So before we got this green state down here, and then it goes boom, or our gas gets hot, and the gas expands, right? As it's expanding, you still have atmospheric pressure that is pushing down on this piston, right? We've got a pressure force per unit area, so there's a downward force that is being applied. Right? You have now displaced something through a force, right? That is the definition of work. And so the work is going to be force times the distance, or in this case, we're going to convert force into minus P times A times D, the displacement, or we're going to say that work is going to be equal to the negative P times the change in the volume. Right? So our piston is going to move a distance delta H, right, or D. So our work is going to be force times delta H, or P Pressure times the area times delta H. The volume of the cylinder is equal to the area of the piston times the height. So our change in volume, our delta V, is going to be our final volume minus our initial volume. So our area times delta H, substituting in delta V is equal to H times area times delta H, gives the magnitude of the work needed to expand the gas against a given pressure. All right, so for a given amount of work, right, you can either push the piston harder, right, move it against a stronger force, or you can move it farther, change delta H. Right? And because this is fixed in a cylinder, delta H, our height, is going to be proportional to the volume change. Right? The opposite of that is compression. So that is work done to a gas. In this case, our change in volume will be negative. W will become a positive quantity because as you compress it, the energy is going in. And the unit of pressure, the unit of measuring pressure, we're going to use 1 standard atmosphere, 1 atmosphere, or 760 millimeters of mercury. Right? So I have a handy little table here that kind of summarizes these guys. So if you've got heat absorbed by the system, it's an endothermic process, Q is positive. If heat is released by the system, it's an exothermic process, and Q is negative. Work done by a system, work done on the system by the surroundings, for example, a volume decrease, W is positive. Work done by the system on the surroundings, W is negative. Right, so this is using delta E is equal to Q plus W, where Q is the heat and W is the work. So let's get an example. A balloon is being inflated to its full extent by heating the air inside it. In the final stages of this process, the volume of the balloon changes from 4 times 10 to the 6th liters to 4.5 times 10 to the 6th liters by the addition of 1.3 times 10 to the 8th joules of energy as heat. Assuming that the balloon expands against a constant pressure of 1 atmosphere, calculate delta E for the process. Okay? So convert between liters and atmospheres and joules. Right? You're going to use 1 liter times atmosphere is equal to 101.3 joules. Right? So I want you to, if you are taking notes while you're listening to this, put a star next to this. Right? Because I think this is the only place this conversion factor shows up. Right, so if you're trying to do one of these calculations with work is equal to, when you get work is equal to P delta V, right, you're going to need this conversion factor in there, and it kind of doesn't show up in that equation. Right, so make a special note of this. Right, so our solution, we're going to calculate delta E. The information we have available is our initial volume is 4 times 10 to the 16th liters. We've got our Q, that's our energy change. We've got our P, that's our pressure. We've got our conversion factor, liters times atmospheres into joules. And then we've got our second volume. So to calculate the work done on the gas, we're going to do W is equal to minus PdV. So to determine the V2, all we do is we do our final minus our initial volume, so 4.5 times 10 to the 6 liters minus 4 times 10 to the 6 liters gives us 5 times 10 to the 5th liters. To determine the work is equal to minus P delta V. So we'll take our 1 atmosphere, this was the pressure we were given, right, times delta V. This is our change in volume that we calculated from over here. Right? And that's going to give us minus 5.0 times 10 to the 5th liters times atmospheres. Right? This unit here, work, wants to be in joules. This unit that we did by calculating pressure times volume is liters to atmospheres. So we then need to convert that, right? We want to get it out of liters times atmospheres. So we're going to convert that into joules by using that 101.3 joules divided by liters times atmospheres. Our liters times atmospheres cancel out. We end up with minus 5.1 times 10 to the 7 joules. So when we add them all up, we're going to do delta E, our change in energy, is equal to our heat plus our work. So we get 1.3 times 10 to the 8th joules plus negative 5.1 times 10 to the 7th joules, because it was expansion, right? We lost that work out into the system to blow that balloon up, or 8 times 10 to the 7 joules. So let's do a quick concept check. Determine the sign of the change in energy for each of the following listed conditions. So if we have an endothermic process that is going to perform work, Right, so if it's an endothermic process, right, it means that our delta H or our Q is going to be positive. Right? Now, if it's going to perform work, our W is going to be negative. Right, so if our work is bigger than our heat, then our overall energy change is going to be negative. If our work is less than our heat, then our energy change is going to be positive. Right? If work is done on a gas, right, so our W will be positive, and our process is exothermic, Q is negative. If our work is bigger than our heat, our change in energy is positive. If our work is less than our heat, our change in energy is negative. Now, it didn't have the other two cases, right, where I've got work is positive and our heat is positive, or our work is negative and our Q is negative, right? In this case, it's always going to be positive, and in this case, it's going to be negative.